No, I get it. I get it.
All right. So in your notes, and I need to turn this on. In your notes, you're going to see the next section is Avogadro's principle. But I think that fits in a little bit better for the next. So we have three things that we still need to cover for this chapter. We have to cover ideal gas law. We have to cover Avogadro's principle, which then leads into gas stoichiometry. Okay. And I think the Avogadro's principle fits better into gas stoich. So I want to do ideal gas law. So if you can skip in your notes to where it talks about ideal gas law, that's where I want to be for today. So if you can find that section, that's where we're going to start.
Okay. Oh, I have the packet. Okay, yes, I see it.
Okay. All right. So, so ideal gas law essentially is going to be able to take into account our pressure and our volume and our temperature from the three gas laws we talked about earlier. But it also takes into account one other thing, which is the amount of gas that's actually contained in there. So this is the pressure of the system. This is the volume of the container. This is going to be the amount of gas in that container. And we measure that. It has to be in moles. We have something called a gas constant, which will always be given to you. You don't have to have it memorized. You might accidentally memorize it along the way. And then you have temperature. Okay, so the gas laws can be combined, like I said, into one expression that accounts for all four variables. At this point, we've just been talking about three of the four variables. Okay, and it takes into account that number of particles. So it works for ideal gases. Okay, now what is an ideal gas? An ideal gas is where we don't have any or very few intermolecular forces involved. Okay, so in an ideal gas, that's the way that is.
Good.
All right. So when we look at this, we're adding in that variable, which we call n. So you will see many places along the way, and if you take AP Chem, you're going to see this in several different formulas where they use n. That's going to represent number of moles. So you'll see that in mole fraction. You're going to see that in Faraday's law when we look at moles of electrons that are being used to generate current through a battery. So you'll see that in a lot of different places. So that's going to be talking about moles of particles. And then the other gas laws just kind of assume that you have a given amount of gas and you went with that. Okay, so that was kind of a weakness on their part. All right, what this is P is pressure, V is volume, N is number of moles, R is a gas constant, which we'll get to in just a second, and T is temperature. Now, let's look at this gas constant, okay? The difference between these gas constants is what your pressure is given in. So if your pressure is given in ATM, you're going to use this number. If your pressure is given in kPa, you would use this number. If your pressure is given in millimeters of mercury, you would use this number. If you look at this gas constant, the other thing that you need to see is that it uses, as part of this gas constant, it's using liters here, which means that your volume has to be in liters. Or if you solve for volume, the unit for that volume will be liters. K is your temperature. So your temperature has to be in Kelvin in order for this problem to solve correctly. All right. So this is an ideal gas law. Ideal gases have no intermolecular forces. Ideal gases follow a gas law under conditions of pressure and temperature, but in reality, no gases are ideal. They behave ideal under different pressures and combinations. But if we assume they're ideal, the math works out a lot easier. So everything's ideal in this class. Okay. Gases behave real when the intermolecular forces increase, when space is between particles is limited, and at high pressures and low temperatures. And this is a real common thing that they will ask you about, is high pressures and low temperatures. And we'll talk about that in this. Did you have to write these down? Okay. All right. So if you think about it, if you have high pressure, okay, the high pressure is going to cause the particles to get closer together. If they get closer together, then it has a better chance of those intermolecular forces working. At low temperature, your particles are moving slower, so they have a much better chance of kind of linking up and hooking up. Okay? All right, so polar molecules behave less ideally than nonpolar because they have more intermolecular forces that they're capable of. And then larger molecules also are less ideal. All right. We can also substitute and solve for molar mass here, because remember that moles equal mass over molar mass. So we can substitute that in for our ideal gas law. We'll come back to that in one of our practice problems. All right, let's get started solving some of these. See if my pen's going to work on here or not. Nope. Let's try to get this working. Pen. There we go. Remember, our formula is PV equals nRT. They're asking us for the number of moles here, so we're solving for N. So I'm going to divide both sides by RT to get N by itself. So N is going to equal PV over RT. And then we just start plugging in values. All right, so our pressure is given here. You should start getting used to seeing ATM. ATM means pressure. So that's going to be my 3.81. Okay, so I'm subbing in my pressure here. Now I'm going to sub in I'm going to get rid of this so we don't get confused by all of this here. Because we've rearranged that equation down here. Okay. Let's see if I can pull this guy up. There we go. Okay, that's better. So my V is my volume. I need to check and make sure that that is in liters. It is, so we're okay to go ahead and use that. Then I need to figure out my R value. So I'm going to go back to my chart of R values here. Notice that my pressure was given an ATM before. So I'm going to use the R value that has ATM with it. Okay, so I'm going to use that value. Is it 2, 1? Okay. And then I need to multiply that by temperature, but the temperature has to be in Kelvin. So I've got to add 273 to this value. So that makes that 278, or 298, excuse me, 298. And then I just go through and do my math. So 2.81 times 0.044. Remember, when you go down to the bottom, if you hit divide, you have to hit parentheses and put in your 0.0821 times 298 into your parentheses, and you should come up with and we need 2 sig figs, so 0.069, and this is moles of gas, so that's moles of, and it doesn't say what kind of gas, so we'll just put moles of gas. Good? All right. Let's see if you can plug this into that formula. You are going to have to convert, you don't have to convert anything, I guess, because well, once you get your Kelvin temperature, you have to convert it into Celsius. See if you can get that set up and figure out how to plug in your values and solve for that.
How are we supposed to convert it to?
Well, have you got your answer yet? You're going to solve in Kelvin in this. You're going to solve in Kelvin.
So is that in Kelvin?
Well, your answer is going to end up being Kelvin. So you're solving for this value right here.
Oh, okay.
When you solve that, the answer will be in Kelvin, and then you just subtract 273 to get Celsius.
Oh, okay. I thought we were supposed to find it before we did the problem. I was like,
No, you can't do that. No.
I was like, that's not possible.
No.
Okay. Is it just 143 on the top, or does the 1 point?
Well, you're going to have to multiply it by the 1 here for the volume.
It'll be over something times
The moles are given right here.
2.
Yep.
Oh yeah, 2.49 times constant.
So which constant are you going to use? You've got 3 constants that are listed here.
I can use any of them?
No, you have to use the right one.
Oh, the constant from that chart. Okay. I will use C. 1.314.
Correct. Yep. You're going to
I
use
don't know
this
why
one because your pressure was given in kPa.
Oh, okay. So we're just looking for what? Like,
So whichever, see how you've got kPa written right here?
Oh, okay. So you just look what your
When you look
pressure
at
is.
whatever your pressure is given in,
Okay.
that determines which one of these you're going to use.
Okay, that's easy. That's doable.
So your temperature ends up being 6.91. Did you get that?
Oh, I'm working on
Okay,
it.
put it in your calculator. Make sure that you're getting the right answer out. And then you're going to have to convert that to Kelvin or Celsius.
So to convert it to Celsius, it's minus 273.
Yep.
I got negative 266.
Yep, that's what I got.
I don't need the 0.09 though.
You just need 3 sig figs.
That's what I thought. Okay.
So negative 266 is what your answer should end up
Can it
being.
be negative?
Yeah, Celsius can be. Kelvin can't.
I was gonna say I thought I was like doing this.
Kelvin cannot be negative, but Celsius can. And we get negative wind chills here all the time. Anything below 32 degrees Fahrenheit is negative Celsius.
Okay.
Because remember, Celsius is 0 degrees Celsius equals 32 degrees Fahrenheit. That's the temperature that water freezes at.
Okay.
So anything that's below 32 degrees Fahrenheit, we might have even been there this morning.
Oh, okay.
It was chilly this morning.
Okay, that makes sense. I was like,
You can't have a negative Kelvin though. Kelvin can never be negative. All right, so see if you can calculate the volume here using this pressure.
Do I want it in the temperature in Kelvin or?
It's already a Kelvin, honey.
Like, do I want to keep it like that?
Yeah, yeah, you have to have it in Kelvin. And you know that because if you look back at your gas constant here, your gas constant has that Kelvin listed in it.
Oh, okay. R is 0.08. I got 7.81. Is that right?
So, yeah, it's just the way we round.
Oh,
It's
okay.
fine.
Do you want me to put 0 or?
Well, you just need to have 3 sig figs.
Okay, the only reason I put 1 was because I just rounded instead of the
Yeah,
cutoff,
and
but I don't think it really
it just
matters.
depends on how you clear your calculator. Like I grab figures from up above and bring them down, and so we might be off by 1/100th. Okay, but yeah, it's fine. All right, so see if you can solve for pressure this time.
I didn't get that.
Okay, so what did you,
6.7.
what did you use for your R value here?
0. Oh, I wrote it wrong. I wrote 0. I wrote the 0 to 20. It would be 0. It should be 10821. Yeah, I got that.
Okay, good. All right, we can take this formula and we can kind of rearrange it because we know that moles or N equals our grams over molar mass. Or you could have molar mass equals grams per mole. You're probably more comfortable thinking of it in that terms, right? Okay, remember N is moles, so grams per mole equals molar mass, right? But we could rearrange that and get N equals grams over molar mass, right? All right, so I can sub in for this N value here. I can sub in this in place of this. That makes sense? So PV equals mass in grams times RT over molar mass.
Okay, so mine says PV equals MRT over 1.
Right. Yeah, it's just grams. I've replaced it now because I wanted you to think in terms of grams or mass. Mass is grams,
okay, so
right?
The M is little m.
That's mass.
Oh, it doesn't.
Mass in grams. Okay, ready? So here we're going to be solving for that mass value. So we had, when we had our thing over here, we had PV equals MRT over MM. We need to get this little m here by itself because that's what we're solving for. So algebraically, I'm going to multiply both sides by MM. That's going to give me PVMM equals MRT. You keep up with me with the algebra there? Okay. Then I'm going to divide both sides by RT to get M by itself. So that gives me my formula for what I'm going to be working with to solve this problem. So now that you have all of that and you have your formula rearranged, see if you can solve for our grams. We're solving for this M here. See if you can do that.
Like the bigger and bigger and smaller mass.
Yep. So that is this value right here.
I got the same thing you did.
Okay, good. All right. Density. Let's see here. I think, let's check your homework for tonight. See if density's in that one. We may just break and we're gonna have a lab probably the next time you come in.
Maybe I'll be the person doing the lab.
Yeah, I can help you if, yeah, Avery's probably gonna be back. I would guess she's gonna be back. I'm not sure about Mia yet, but Avery I think will be back. Oh, wrong chapter. Let's try this again. So ideal gas law worksheet. So for your homework tonight, you should have this. I believe this is your homework, right? Does this look right?
Yes.
Okay. Moles, pressure. Yeah, you should be able to do all of these done. So this is your homework tonight. Get that done by tomorrow. And then the next time I see you, we'll do the ideal gas law lab. I'll get that run off next hour. So that is our game plan.